So today we are dissecting the mechanics of hydrocarbon injection. So by the end of this session, you will walk away with the four critical deliverables. First, an understanding of the thermodynamic engine known as RAFT. The second, a technical comparison of gas versus coal infrastructure. Third, the kinetic advantage of hydrogen over carbon monoxide, and finally, the economic break-even logic of coke displacement. So, on the left side, as you can see, follow the blue and orange gradient in our furnace cross section, the indirect reduction scale. In the stack shows our exothermic zone, while the direct reduction scale at the bottom highlight the high thermal endothermic demand of a smelting. So what factor is here is engineering constraint. Your carbon injection is strictly limited by the energy balance at the tuyeres and the reduction efficiency in the stack. So to maintain that energy balance while injecting cold hydrocarbon, we have to master the adiabatic engine of the raceway, and that is all about the flame. So flame control about is because it becomes most important, and that is what we are saying in control. So coming to the slide number 2, which is about a controlling shaft, that is the thermodynamic engine of the raceway. So this is your master dashboard, which is shown on the slide for the raceway stability. The orange bars on the left shows the heat adders, the hot blast temperature and oxygen enrichment, providing the thermal energy to superheat the metal and slag. So these are the basically accelerator. So on the right, follow the blue descending steps. These are your heat sink, including blast moisture and their injectant like PCI or natural gas. So notice the impact. Natural gas has a massive cooling effect of around 24, more than rather 24 Fahrenheit per unit, while PCI is much lower at 6 degrees centigrade Fahrenheit, directly at the application. So what is critical? Hydrogen injection fundamentally lowers the flame temperature by a big margin. To maintain the 3600 Fahrenheit to 4000 Fahrenheit required for a stable raceway dynamics and silica reduction, high level of fuel injection mandate simultaneous oxygen management. So without balancing this waterfall, your heart will chill and your slag will lose its fluidity. So balancing this thermodynamics is one challenge, but the physical architecture required to deliver this fuel represent a massive chemical divergence. And this is what is most important for us. That is about a system architect. As you can see that is the simplicity of this architecture versus those coal infrastructure. This totally things are shown on the slide number 3. So on the left, the natural gas setup is the definition of simplicity, just a 2-inch steel pipe and a in-corner lance. It's cheap to install and easy to control the basic flow meters. So now look at the pulverized collision injection or PCI architecture. It is a massive industrial complex involving conveyor, pulverizer, cyclone and bag filter. The PCI infrastructure represents the two-thirds of your total project cost. The technical requirement for the coal is intense. It must be pulverized to 80% minus 200 meths, as we all know. So what factor is operational overhead? So while gas is set and forget, PCI requires a specialized transfer vessel and uniform tier supply distributor to the prevent clogging. So you are trading low raw material cost for high maintenance and capital intensity. So beyond the pipe and the pulverizer, the choice of injectant dictate your chemical efficiency and your replacement ratio also. So the injectant trade-off matrix, as you can see, this table is your cheat sheet for the fuel selection. We are comparing natural gas, fuel oil, tar and coal across the five technical dimensions. So look at the S2 by C ratio column. So natural gas leads to the pack at 0.32, while the coal is a distant 0.06. So now correlate what the replacement ratio. Natural gas yield 1.4 pound coke replacement, while coal only achieve 1.0 ratio. The so what factor is the chemical versus cost trade-off. So coal is the cheapest material but has the slowest kinetics and leaves behind uh, char or uncombusted carbon. So natural gas offers the cleanest chemistry and fastest combustion but carries high endothermic penalty. So as a manager, you are not just buying the fuel, you are buying a specific combustion speed and a specific hydrogen to carbon ratio that will dictate your furnace internal breathing. So that breathing is physically enhanced by the unique fluid dynamics of the hydrogen and oxygen, and which is our slide to also focus on that. That is about our chemical catalyst, the fluid dynamics of hydrogen and oxygen. So slide illustrate the virtues of the cycle of hydrogen. So follow the circular flow, injecting hydrocarbons like methane produces hydrogen, which has a massive kinetic advantage. Hydrogen diffusivity at 2000 Fahrenheit is 10.5 centimeters square per second. So more than triple that carbon monoxide. So this lowers boss gas molecular weight by 14%, dropping it from 28 to 24.1. So again equation impact on these, and due to the lower gas density reduces the upward force of the gas, which significantly decreasing burden hanging and improving the permeability. So this allows us to push even higher injection rate and more oxygen. So we use hydrogen as a chemical catalyst to thin out the gas phase, enabling us to drive the furnace harder while maintaining a stable descending stock line. So it's the ultimate tool for the unlocking productivity. So all these technical levers finally converge on a single economic reality, the break-even threshold of production. So coming to our main slide, which is on the economic synthesis, that is production velocity and cost efficiency. So we have concluded with the economic synthesis, and this graph maps your path of profitability. So line 1, the coke displacement curve shows the coke rate dropping inversely as you increase injection. Line 2, the productivity multiplier, which also scales the linearity with oxygen enrichment up to 16%. So this is your economic break-even threshold. Injected only yield saving if their cost typically 50 to 100 US dollar per ton is offset by displacing highly expensive coke. The so what is the system limit. So if you push injection too far without enough oxygen or permeability, uncombusted soot and char will erode your saving. So optimal operation is not simply maximizing injection, it's a precise, dynamically balanced matching of the fuel chemistry and burden permeability to maintain the thermal blueprint.